Welcome to State of the Science, a new way of talking about research in the field of type 1 diabetes. We have a global audience of scientists here today, and we thank everyone for joining. We'll first talk with 4 scientists who will anchor the discussion and set the stage for the discussion, and then we'll interact with the audience a little, and then the panelists will join to extend our conversation and again engage with the audience. And we'd like to take a moment to recognize our fantastic sponsors. I'm sure you've heard of them, 10x Genomics, Vertex, Prevention Bio, IMSICE, and Inspiro. These organizations are at the forefront of cutting-edge science, and without their support, we could not bring you State of the Science. You can find more about these innovative companies on our website or at our Ask the Expert series, both live and archived on our YouTube channel. A few pro tips for attendees: to submit a question, place it in the Q&A. You can submit questions throughout the presentation, and participants can upvote favorite questions. At the end of the session, we'll answer questions as time allows. This event's being recorded live on the Sugar Science YouTube channel and will be housed there after for further viewing. So thanks, and without further ado, let's begin our introductions. I'm going to introduce the 4 scientists who are going to set the stage about what is the most promising approach for beta cell replacement at the moment. Dr. Cherie Stabler from University of Florida. Her research centers on engineering of cell-based tissues for the treatment of type 1 diabetes. Felicia Pagliuca, PhD from Vertex, Vice President Disease Area Executive for T1D. Ekaterine Bershivili, MD, PhD from the University of Geneva. Currently, Dr. Bershivili and her group are focused on the development of a bioartificial pancreas. And Douglas Melton, PhD of Harvard Stem Cell Institute, has a goal of curing type 1 diabetes using islet cell implants. And then the next set of well-known scientists have a deep knowledge in the field of beta cell replacement, and they're going to offer their opinions and ideas in sort of a town hall style once the anchors set the stage of the discussion. And these scientists are Naji, PhD from PENN, Mike Rickles, PhD from PENN, James Shapiro, MD from University of Alberta, Peter Butler, MD from UCLA, and Mark Atkinson, PhD from University of Florida. So let's just start it off. Dr. Bershivili, would you like to set the stage with your impression of where things stand in terms of beta cell implants now and going forward?
Hello, everybody. Hi, Monica. Thank you for inviting me. I'm delighted and happy to be here. So before we begin where we stand now, let's look a little bit back. What we have done already, and it started in 2000 when there was the real breakthrough in the new regimen of the immunosuppression, and islet transplantation became available for a more wider range of the patients, and now we can offer them the islet transplant into the liver. So the islets are transplanted in the liver, but we still have the problems. What kind of problems we have is we should fight against the inflammation that takes part against the source of the islets. We don't have enough tissue and cells to transplant. We have the huge problem with immune suppression. So these are the hurdles on the right now in the clinical setting, and then we have to improve. But the problems don't start from the transplantation. Problems, they start before, when we isolate islets. So we isolate islets. We have different kinds of islets. They are vary in size. So we isolate from the extracellular matrix. The islets lose their vasculature, their contacts with the endothelial cells, which are detrimental for the islets. They lose the extracellular matrix, which is again detrimental for the islets. So, and we see the huge course, necrotic course in the cultured islets, and these kind of fragile and damaged islets are transplanted. So the first days there is no vascularization. The islets, they survive solely by the diffusion of the oxygen and nutrients they have to penetrate. So bigger islets, of course, they are eliminated. So we need to achieve insulin independence. We need several donors, 2-3 donors per recipient. So usually this is the reality, and on the basic, we see the problems down and we have to come up with solutions. So that's what we are working in our group, for example, and then many other groups. So we work on that to improve the function of the islets with the generation of organoids. There are other groups who are working on expandable, replenishable sources of beta cells from the xeno sources or from the pluripotent stem cells. We also work, and others, on the biomaterials like hydrogels, extracellular matrix molecules, to provide them to the islets and to improve their viability and function. And then they're on the immune, protecting them from the immune attack from the recipient. This can be done, and the many groups are working on the mechanical protection, encapsulation of the islets, and some, including us, we are working on biological protection through the incorporation into the organoids, some cells that are genetically edited, and they can modulate immunity. This is where we are going to, and we're trying, and others also trying to develop bioartificial pancreas that can be transplanted to the bigger and wider, to all diabetic patients without immune suppression. That's the main goal of many of outstanding groups working on this problem. I hope I did not exceed the time given to me.
No, that's totally fine. No, it's good. It's good to get sort of the landscape, and especially to understand sort of what's happening over there in Geneva and Europe. I think that's it's really important. And, so thank you so much for, kind of setting the stage there. And I would ask, like, Dr. Melton and Pagliuca would like to weigh in together on that same question from Boston.
Felicia, why don't you go ahead and start?
Sure. Thanks, Doug. And thanks, Monica. It is a real pleasure to be here with so many amazing scientists in this field. I'm a scientist and entrepreneur myself, and spent years working on developing stem cell derived beta cells with Doug, first as a postdoc and then at Summit Therapeutics, which is now part of Vertex Pharmaceuticals, which is where I'm joining you from today, where I lead a cross-functional team that's dedicated to the translational work of bringing stem cell derived islets into the clinic and beyond for people living with type 1 diabetes. So perhaps I'll start this with 3 points, some of which I think overlap really nicely with that of the first speaker. And the first is, when you think about cell therapy, type 1 diabetes is really remarkable. One, because we understand the causal biology so well. We understand that this missing cell type, the insulin producing beta cell, is really at the heart of the disease. And to truly modify the course of the disease, we know we're going to have to find some way to replace those cells. The second piece of that that's interesting from a cell therapy perspective is that there is this remarkable clinical proof of concept from cadaveric islet transplantation. And you can really think of very few other diseases that are being approached with the cell therapy type of medical approach that have that level of clinical proof of concept, that if you can put the cells back, if you can protect them from destruction, as we talked about with systemic immunosuppression or something else, that you have a chance to leave people insulin independent. I think that's a really remarkable and important point when you think about regenerative medicine and the place that type 1 diabetes is at the tip of that spear, I think. The second point I'll leave you with is the state of, I think, the stem cell science, which has really remarkably evolved over the last decade in particular, and our ability to control cell fate, now not just at a small scale, but at larger and larger manufacturing scales that make it feasible to generate the kind of cell doses that you heard about that you might need multiple organ donations to achieve in order to get to the level of cell replacement that you need to achieve the clinical outcomes that we're all hoping for. And I think as we move into this translational space, the control of CMC, the control of manufacturing in terms of getting the composition of those cells right, in terms of getting the consistency of activity right, in terms of getting the scale and all other components of control correct, has really advanced, I think, remarkably over the last decade. And then the last piece I'll leave you with is coming back to this immunology challenge, which is the next frontier. And I know something that Dr. Melton will speak about as well. And there, I think our toolkit is expanding for what we may be able to use in order to protect these cells from destruction. So if we can solve the cell supply issue with a stem cell-based source, then the focus really turns to the tools that we have to protect those cells from destruction. I think there's enormous value in immunosuppression and in fact, an expanding understanding of immunology in the solid organ transplant field that I think will become increasingly important and relevant for islet transplant as well. Then you have encapsulation, which is similar level of advancement over the past years in the ability to encapsulate cells in a manner that minimizes the foreign body response that has been such a challenge to the encapsulation field. And then the third piece in terms of approaches to the immune problem, if you think about pharmacology, if you think about encapsulation, is the ability to actually modify the cells themselves with all of the new gene editing tools that we have and the understanding we have from other parts of biology about what are the molecules on the surface of those cells that may be triggering the immune response, participating in the immune response, and how can we leverage those insights from other fields to bring forward a cell therapy that doesn't trigger the same kind of inflammation or outright allogeneic or autoimmune rejection. And so I think it may be the case in the coming years that it's a combination of these tools that allows us to really break through in delivering a cell therapy to the largest population of people that we can.
That was really well said. Would you like to add something to that, Doug?
Yeah, as you say, it was so well said. I'm trying to think of what I could add that makes it sound interesting. Maybe I'll just give some more editorial comment to say that I think this is a very exciting time, maybe because I'm sort of simple-minded about it, but I think the time of using cadaveric islets, closed loop systems, improving insulin is largely over. I'm glad people are trying to do that. But it seems to me resources should be spent on what Felicia said, which is you have a drug product that you can control. So you're not dealing with the variation of cadavers and enzymatic isolation. You can make a defined drug product. Now, that doesn't mean it's possible to make it now in the best possible way, but it does mean that that's in sight, and that's where emphasis should be put. So if I move to the immune system, I don't know much about biomaterials and bioengineering, but I'm glad people are working on different encapsulation devices. And I think those are likely to be used in the next few years. But the long-term solution, as the two previous speakers said, is to think about using genetic modification so that you can transplant allo cells into a type 1 diabetic and not have them rejected. And what hasn't been mentioned yet, but I know others have thought about it, is there are numerous instances where the body can accept cells from another person in the absence of immunosuppression. For example, microchimerism and maternal-fetal interactions. So we know that biologically it is possible to have cells inside of you which are from another person. What we don't know is how to manipulate the genes to accomplish that. I'll finish by saying, I think there are two kind of approaches beyond encapsulation for dealing with the immune problem. And clearly what I'm setting aside here is what Felicia and her team and others are going to solve, which is the manufacturing problem. So what are those two approaches? One of them is to think about what you might do to manipulate the immune system of the recipient. And there are lots of companies and others working on Tregs and other kinds of cells to, let's say, fool or manipulate the immune system so that it'll accept the cells. The version of that, which I like most, is to genetically modify the drug product, is to change the cell you're putting in so that it will, at a minimum, modulate and maybe even evade the immune attack. No one knows how to do that yet, but I think that's an exciting area, open to lots of discovery. And so I don't mean to imply that other speakers weren't enthusiastic, because they were, but I think this is a great time in the field. I mean, the ability to make functional beta cells from an unlimited source of stem cells is a game-changing phenomena for the whole field. And I'm delighted to be on the call with people who know more about the sort of practicality of that than I do, Dr. Shapiro, Dr. Naji, and others who've done this. And so I might finish my comment by saying, what do I think the challenges are? They're dealing with the immune system by genetic modification, figuring out where to put the cells. I don't think we have a clear idea yet about where the cells will be happiest and how long the cells will last. I might just end by saying, I'm amused in the case of my own children. When I ask them, how long do the cells need to last if you put them in? My daughter says she's ready to go in once a month for new cells because she's so sick of the disease. And my son says, well, they have to last at least a couple of years before I'm going to try it. And so I don't know what the right answer is, but how long the cells will last is something we don't know. And I think that's an important problem. So I thank the first two speakers for giving a more professional view of the whole field. And I just sort of added my editorial comments to what I think is exciting. Thanks.
No, that's great. The editorial comments are important, and that's something we really kind of try to celebrate here, is just to really speak freely in an editorial way is a great way to put it. And so Cherie Stabler, what are your thoughts on this? What's the state of the art, and how do you frame it?
Yeah, it's hard to go after such three amazing summaries. And I think I definitely echo everyone's sentiments, particularly in terms of being excited and also the potential. I think Felicia's made an excellent point that the fact that cell therapy can take some of the most, poorly controlled glycemic diabetic patients and make them insulin independent is amazing. It's what drives me every day to go to work, is I know that potential is, and being able to be on the panel of some people that contributed to the success of CIT is just an honor. But, we've learned so much about the potential of that through so many patients that have been willing to participate in these clinical trials, and, thanking them for their contributions to science of what we've learned. So I think we know so much about the potential of the cells in treating type 1 diabetes. And I think, echo a lot of people's sentiments of we need to address the immunological challenges and also where we're going to put them. With other organ transplants, we don't have this luxury of just kind of thinking, where should we put them? If it's a kidney, we have to hook up the plumbing. But I think sometimes with this luxury, we get a little, well, let's just put them anywhere. And we can't just put them anywhere. We have to really think about what these islets need. The reason why they're in this niche within the pancreas, why are they these little islands? They're only 1% of the pancreas, but they get, a huge disproportionate amount of blood vessels and perfusion. We have to really look at that architecture and look at those needs in the design and make sure we try our best, not to completely mimic that, but really think about what are those key parameters and design it. I'm an engineer, so I'm thinking from an engineering perspective, what are the key engineering criteria that we need to meet to meet the demands of these cells? So, we don't necessarily have to put them, back in their little islands in the pancreas, but we also don't need to just simply inject them in random places and expect them to survive well, particularly because they don't just need to secrete insulin. They need to respond to glucose and secrete insulin in a very dynamic manner, because there has been tremendous advancements made in the artificial pancreas. And we don't want to create a golden hammer that, just is 1,000 times more expensive than an artificial pancreas, but does maybe as good, because we've lost a lot of that glycemic control. So we do have a lot of challenges in terms of identification of a site. I'm very encouraged by a lot of work that's going on in many different labs that are identifying and engineering the site. I have a lot of hope for once we get these cells out of the liver, where they're kind of scattered throughout and we have a lot of lack of control over their microenvironment, that we can put them in a confined site. And that really opens up the door to be able to create things like vasculature and recapitulation of their native niche, as Ekaterine talked about, as well as the immunological challenges, is thinking outside the box of, instead of systemic immunosuppression, which immunosuppresses the entire patient, can we create this zone, or maybe even this instructional zone? And we've learned a lot from cancer immunotherapy that we can use these tools to instruct the immune system to do what we want it to do. And so maybe we can really leverage this microenvironment to instruct the immune system to not necessarily not attack, but maybe even accept this graft. So I'm excited a lot about new things that are coming out. And then the other thing that I'm very enthusiastic about is this continuing shift in how we do science from a very collaborative perspective. I think a lot of us want that collaborative network. Treating type 1 diabetes is a multifaceted problem. And myself as an engineer is going to come from a very different perspective than a cell biologist or immunologist or clinician. And I think having these multidisciplinary teams working together to address this challenge and being very targeted and focused on what the key goal is something that happens a lot in industry, but doesn't happen enough in academia. And I think that the funding agencies, JDRF as well as NIH, are really focused on trying to build these teams. And I think that's really showing the fruits of that labor to having these innovative approaches that are coming out because of this multidisciplinary approach.
Yeah, that's great. Well said. I feel like the whole, because it's so multidisciplinary, this disease, and there's many different types of scientists studying, so important to get them all in a room and sort of cross-pollinate each other's ideas. So yeah, I love what you just said. Did I cut someone off? It's talking. I'm going to do a quick poll to our audience. We're going to ask, here's our poll. Which, let's see, which types of cell types are absolutely necessary for an optimally functional islet implantation? Alpha, beta, delta, epsilon, PP cells, exocrine cells, plus all of the above, all of the above. So let's see what happens. See what people say. There's been a lot of talk recently about the influence of the exocrine pancreas on islet functionality. So, right, everyone's sort of hearing that, and we'll see what people say. Oh, beta's in the front, way out in front. That's interesting. No one cares about the PP cells or epsilon cells. Well, some people do. But yeah, so let's see, almost everyone has voted, 67%, 70%. I'll go to 75% voting. People are taking their time and thinking closely. Yeah, so beta cells are way out in front. I'm a little surprised about that. I thought maybe people might say all of the above. But definitely alpha and beta are out there. Okay, we'll stop it at a minute. So what are people's thoughts? What are people's thoughts on this poll? And I would say, maybe sort of the four anchors. Can you comment on these results? Nobody can?
Maybe just my uninformed opinion is that we should just worry about alpha, beta, and delta cells and find the right composition of those for the transplanted cell therapy.
Okay, on from there.
I agree with Doug. I think those are the fundamental important in terms of homeostasis. And we still really don't know much about the contribution of a small fraction of endocrine cells. But I think most of the evidence, either at the experimental level and human, shows that those 2 or 3 cells are really, really important in terms of feedback.
Mm-hmm.
If I may add, absolutely, I agree that alpha and beta and alpha cells are mostly important, and maybe the somatostatin producing delta cells also. But what I think, and it's my very strong feeling, and not only based on the evidence, that endothelial cells that are not listed there should be also incorporated, because the crosstalk between endothelial cells and the beta cells are crucial. So VEGF that is produced by the beta cells is attracting endothelial cells and feeding them, but on the other side, endothelial cells produce laminin, which is crucial for the proper function of the beta cells. So this was proven many times in the experimental settings. So, and I do think that accept a part of the endocrine cells, we should also think to incorporate. There were works that were showing that the necessity of macrophages even, how they can influence the function of the beta cells. So this combination and interaction between these cells, we should also consider islet as a mini organ. We should build the organ, not just the combination of the cells. This is my,
Monica, can I make a comment quickly?
Yes.
This is Mark. Okay.
Hi.
Thanks again. Hi. So I think, as Doug and Ali said, you know, if you take it at simplest basis, that when islet transplant works, you achieve success. And that makes an argument for the cells, endocrine cells, to actually be important, and maybe downplay the exocrine a little bit. So that, I mean, that's a simplistic answer. The one thing that wasn't on your chart that's getting growing appreciation has to do with the innervation of the islet in its responses to neuronal stimuli. And again, it's a field that some would say is its infancy. Some would say we've known a lot for a long time, but it could prove over time that has some influence. I don't know how great, but that was all I wanted to say.
Yeah.
Mark, that's a good point, but I want to, at least on my side of it, echo what Cherie said, which is we don't have to have perfection. We have to get better than a pump and a continuous glucose monitor and the inconvenience of having those two machines attached to you all the time. So that's why I say getting the 3 cell types is going to be more than good enough. We're never going to get perfection and make it like people who haven't had diabetes, but we can have a dramatic change on both the health and the lifestyle of people by transplanting those 3 cell types. And I think that was Cherie's point, is that what is our challenge? It's to get better than a pump and a continuous glucose monitor. Isn't that what you were saying, Cherie, or did I misinterpret what you said?
No, I think you, yes. And moving the needle forward and trying to, I think, you know, what's moving forward in clinical trials may not be the ultimate end product, but I think we'll learn a lot from that and learn how that then is better than a pump, or, you know, is it equivalent? And then how do we make it better? You know, so I think we can look at every single aspect and say innervation is important, and it is, endothelial cells are important, and it is, all these things are important, but you obviously can't do it all at once. So I think all these studies are very, very important for us to understand and try and make things better, the product better. But yes, we do have to manage both creating a functional hammer that maybe doesn't look so pretty, and the golden hammer that nobody can afford, that may be perfect. So, or maybe overkill for it.
Spoken like a true engineer.
And I'll just add, I agree with Doug in that, and I wish that was a better part of the messaging on this area, that we have to start somewhere. And even if you look at the history of insulin, I mean, the first insulins that they made looked something like sweet iced tea in terms of color. And then they got clear and more pure, and then recombinant, and then analogs. But yeah, so you got to start somewhere and walk before you run. So good, very good point.
I would also add, like, you know, for the 3rd session of this, we had the EPITA crowd on there, all surgeons basically, and they were very much all about, like, look, we can take a pancreas, we can put it back in and it works. We don't, and it doesn't need innervation. And then at the same time, you know, there is that whole body of work that came out of Philippe Blanco's work in France, and Matthias von Hereth also showing that the pancreatic nerves, vagal nerves, sympathetic nerves have some major impact on the start of type 1 diabetes. So yeah, I mean, I think, yes, it's almost like you have to build something that's functional, that works, at the same time still continue to really understand how this organ works. So yeah, it's great. I think
can I add something?
Yes.
This is James, just to ask maybe Doug and the team, and thinking about your children, Doug, and how frequently we might need to replenish these cells. What about progenitor cells within the organoid mix? Are they important or not?
I think not. And first of all, I think the idea that there are endogenous progenitors in adults, as you may know, I don't think that's a viable idea. I think if there are progenitors, they're left over from the differentiation protocol and they haven't kind of moved along. So I don't think they'll cause any harm, but I don't see any advantage to including progenitor cells. But thanks for the question. Since you asked one, if Monica will allow, I wanted to ask you and Ali as practitioners, if the group could present you with what we can demonstrate is a fully functional endocrine organ, as others have said, containing alpha, beta, and delta cells. Let's just assume that that's possible. I agree that we're not there yet, but that's coming. Where would you ideally put them? Do you still like the liver? Where do you think is the ideal place to transplant the cells?
Well, so the maybe the emotive word is ideal, and maybe we don't need ideal.
Okay, how about
So
preferable?
Preferable. So
Okay.
I like the liver, obviously. I've used it in 700. We've done over 700 intraportal infusions in patients. I find it to be a very safe and effective place to put cells. It may not be completely efficient, and maybe it can be further optimized. And I completely accept all the challenges with trying to find out what's happening with the cells and the biology and all the rest of it. But I think creating a cell like you've done, and being able to place it in an environment where it can survive is clearly important. And I think the efforts to place cells subcutaneously was enabling at the beginning, but I think now is really limiting our ability to move forward. So I think the liver is it maybe not be 100% efficient. It isn't, but it does accommodate full endocrine cell function. And we have some patients. We've got some patients now that are 21 years insulin free with the original transplant. Not many, but a few of those. So I think that the liver can act as a very effective site for implanting cells, and by all means we should work on other better, more vascularized, more efficient sites, and we'll get there, but I don't think we are there yet.
Okay, just want to make a couple of comments. That first of all, it's been outstanding, everyone's thought process with this really challenging times, but I absolutely agree. These are exciting times for cell therapy. But a couple of personal observations. If you really look at the poor weighted cells, when we put solid organs, as Cherie said, we hook up the pipes in the liver or a heart or the lung or a kidney, and they get blood supply. Just for a second, I've been thinking these poor just islet cells that have been through this gyration of centrifugation enzyme, you put it in this little sinusoid or little caves of the liver, and there is no engraftment. I mean, this is amazing. Even with that, we still get outstanding results. This is really amazing. So the second thought process that I have is we really are in a decade. At the moment, the field of transplantation is learning a lot from the tumor biologists, particularly those interested in the tumor microenvironment. They are leading. They're leading the science of immunology, T and B cell behavior. So we really are good partners. And what is also amazing, and I think I love, even with solid organ transplants, the one that Jim and I did, we have some people who keep their kidney or liver for 3 or 4 decades, and another group that they said, well, the half-life for your organ is about 7 years. We really don't know why. We treat them with the same immunosuppression that shows the heterogeneity of the immune system. And it is time, with the progress in immunology, we can really get some insight into why some of Jim's patients have maintained a perfect glucose homeostasis for 21 years. The one that I have is for 12 years, whereas other ones drop off at year 4 or 5 or 6 or 7. So we really are in a unique position to do that. But my final thought is that we should take advantage of advances of immunobiology, particularly colleagues that work in the tumor microenvironment. They really are into something. Of course, their mission is opposite to us in terms of stimulating the immune system. And I think our mission is contrary, but I think we can we will continue to learn a lot about that. In terms of sight, I think obviously there are going to be parallel trials. The subcutaneous compartment is very attractive because I believe it will prevent the IPMIR, the loss of the islets. And what is also, at least in our work, to find out mechanistically, what are we doing empirically that's this bunch of islets really getting grafted without any failure. I think that is very important in terms of extending that to other sites, wherever it might be.
That's really good input from those who are actually, you know, kind of hands-on with the islet implantation. So thank you for that. That's really great. I wondered if we could just ask another poll. we've had such a great, rich discussion. We have like 15 minutes left, so I could go on, but I would like to ask this other poll. And this question is, do you think that, I'm going to launch it. Stem cell derived islets, one, stem cell derived islets, or two, transdifferentiation of endogenous pancreatic cells into beta cells is most likely to work for cellular therapy. So let's see what people say. And it's an absolutely, well, I don't know.
Monica, while they're answering, could we get a comment from Peter Butler, who's one of the most thoughtful people I know in thinking about this area and treats lots of patients? Peter, you've been quiet.
Yes, please do.
Well, thank you, Doug. Can you hear me?
I think you might have your phone on and the computer on.
Yeah.
Oh, yeah, that's it.
Can you hear me now?
Perfect.
Unfortunately, yes. I don't think I could be heard.
Yes, we hear you.
We hear you. We hear you, Peter.
It's okay.
I don't think he can hear us. Peter, can you hear us?
Can you hear me? No.
Yes.
Yes. Oh, you can hear me now. I'm sorry what technical issues we had going. We started off in the cafeteria as I met a young student here and came upstairs. My apologies. So, first of all, I actually think that this is a terrific discussion. Doug is right. I see patients frequently, and every clinic they're asking me, when is this going to happen? They're impatient, not just Doug's children, many people. And the closed loop system is great, but it's a long way from being liberated from diabetes. Just this weekend, I was dealing with a couple of patients where pumps failed, where the giving stats got infected. There's this is not liberation. And the other thing that I think is remarkable, as Felicia started out with, we're talking about 500 milligrams of cells that are missing here. That's all we need. Dr. Naji and Shapiro and co are putting in kidneys and livers that are kilograms in size, but all we need is 1/2 of 1 gram of cells. That's all that's required to reverse diabetes. And now that they're being manufactured in such a reproducible fashion that are so nearly mimicking what we need, and great progress being made, as pointed out, with the immunology. I feel like I'm usually very cautious with my patients and promising them that there's a way forward for this because they've been promised this for years and years. But now I am telling them, stay well, stay healthy. This is within sight. So my job here, as Doug knows, is mainly to be a cheerleader and a link between patients and to cheerlead you guys who are doing the work, because it's really, it is very exciting. It is within reach. Perfectly agree, imperfection in terms of beta cell composition, alpha cell composition. We put in pancreases with goodness knows what differences between people, they work. So I think, following James' tremendous first step, and James reminds me that he was a medical student when I was a resident, and apparently I told him, when he said he wanted to be a surgeon, I told him do something useful and work on diabetes then. Isn't that right, James?
Absolutely right. Yeah.
I was a resident running around a hospital in Newcastle, and this young medical
Yep.
student told me he was going to be a student. And so I told him, well, then do something useful for a change for surgeons and work on diabetes. So I think that's my single greatest contribution to the field, actually, is maybe influencing James into this. But
You taught me some good medicine too, Peter.
all right. Anyway, yes, I apparently did. But I thank the opportunity. I think we're agonizingly close. And again, just think of that 500 milligrams. That's all we need. I think that's really a critical issue here, that we're that close.
Peter, may I ask a question, Monica?
Yes, of course.
Peter, thank you for the wonderful insights, and Doug. I have a question about what do we know about the senescence of these 500 milligrams?
Here we go.
How do we need, and I think this is really important because at least with respect to stem cell derived beta cells, we have a backup system. But on the other hand, do we know anything, I need for my own education, how these senescence occurs in these beta cells as they're transplanted?
Maybe I can speak to what happens to the adult beta cells, because we studied and published as pancreases in humans out to the age 100. And from the age of about 50, 55, the exocrine pancreas begins to involute and shrink and undergo changes that are senescent. But the endocrine pancreas is remarkable, and the beta cell mass, the numbers of beta cells, remains incredibly constant in healthy humans, or living humans, right out to the age of 100. So that beta cells, like retinal cells, as you know, pretty much what you have is what you keep lifelong. And in non-diabetic humans, they remain remarkably, they really don't we don't lose them barely at all. Since via the process of what Felicia, Doug, and co are doing is putting in new nascent cells, I would be optimistic and think that they would have a potential trajectory. As long as they're not mishandled by the immune system, they should be starting out with a biological clock that would enable them to be long-lived. So I would be optimistic about that not being a hazard.
Thank you.
Thank you so much for that. That's really that's a strong visual. I think will stay with everyone who's listening. The 500 milligrams, right? So that's all we need. So the poll results are back. It looks like stem cell derived islets are the winners. So we can leave it at that. I think a lot of people that are on this call are sort of believers. And I guess I would say, in the interest of, we have 10 minutes left. I'm going to do the last poll, I think, just because we're at
Monica, could I ask a question while you're getting the poll up, particularly for the clinicians who are practicing this? What is your view on transplanting stem cell derived islets into insulin dependent type 2 diabetics?
I personally, let me jump. I personally don't have any problem. I think I personally also have done whole pancreas transplant in type 2 and with excellent results. So I think that is a frontier we need to explore. And I personally, from the standpoint of efficacy, I don't have any problem. Now, of course, one argues about the degree of insulin resistance. It's something that I would love to see what Peter thinks, and Jim.
I completely agree with what Ali just said. I think we can also manipulate the insulin resistance side of things to a degree with some newer drugs in type 2 diabetes that may be used in combination. But you also have the big advantage with the stem cell derived therapies is that you can, the 500 milligrams, you can dial up the dose to what the patient needs. You can titrate. Whereas in type 1s right now, we maybe just give enough cells to allow them to separate from insulin for a period of time. We don't provide a normal complement and reserve of endocrine mass. You could do that, and you could provide double or triple or whatever's needed in patients with type 2 diabetes. They may have to be carefully selected to start with, But as Ali says, these pancreas transplants work very well in selected patients with type 2. No reason why it wouldn't work.
Has the addition of stem cell derived beta cells been transplanted in any animal models of type 2 to date?
Yeah. Tim Kiefer's got data in Vancouver and showing clear efficacy in his models. Yeah, doesn't mean it will necessarily work in patients, but
yeah,
conceptually it will.
Maybe I could chip in on the insulin resistance side, just to remind people that patients with type 1 diabetes are equally resistant to patients with type 2 diabetes. So if it works in type 1, it'll work in type 2. Insulin resistance is largely body mass index based, and we certainly have people who are bigger than ideal who have type 1 and people who are bigger than ideal in type 2, and we have lean type 2s and lean type 1. So DeFronzo, I think, published before some of the participants were born that insulin sensitivity is equally down in type 1 as it is in type 2. It's the abnormal delivery of insulin actually subcutaneously rather than intravascularly contributes to insulin resistance. So in fact, when you transplant patients with type 1 diabetes, and this was shown quite a long time ago, their insulin sensitivity does improve. I believe the Dr. Naji and Dr. Rickles have shown that you improve. They published nice papers on insulin sensitivity in type 1 and the improvement following islet transplantation. So again, the big advantage of cell-based therapy is the insulin's going into the vasculature. So it's minute by minute secretion, and no pump can ever get close to that. That's the absolutely important advantage.
But I think it's probably obvious why I asked the question, which is one hardly ever hears any discussion about stem cell derived islets for type 2 diabetes.
no.
It doesn't seem to have attracted any attention from the commercial side. And I didn't know if that was because there was some clinical reason to think it would not be a good idea.
I think I'm sorry.
Go ahead, Ali.
My own view is a superficial view. I think once we start with the success of the stem cell derived for type 1, to me, it's inevitable that will come. That will be even a mission by endocrinologists and a lot of other scientists that are clinician scientists that are working in this field. In my view, it's just a matter of showing efficacy in type 1 diabetes with hypoglycemic unawareness. I think that's, to me, it's a natural pathway. It will come, but that's my own opinion.
I think, Doug, it just has to be done. Demonstrated proof of concept,
right,
and then expanded.
Right.
Yeah, but interestingly, if the finances were otherwise, it's a better experiment to start with an autologous type 2 transplant. But as far as I know, no one is doing that. I know Peter has expressed interest in that, but I don't know any group that is pushing on an autologous transplant of stem cell derived islets for type 2, which of course eliminates, in theory, the immune problem.
But Doug, isn't that more of a bureaucracy and regulatory difficulties rather than biology?
No, I think it's financial, Ali, because it's so expensive. For every patient, it costs $2 million probably to characterize the cells. I think it's just a financial issue.
But wouldn't you think that that market for type 2 is so much bigger that it would be an incentive for industry to wade into it?
I don't know what the market is. Others who practice probably know. I don't know how much insulin is injected into type 2 diabetics. Is that half of the market or 10%?
Yeah. No,
half.
It depends on the country, and you could say on average. I mean, and there's even people that take insulin and other drugs. I actually, Monica, I think we could have a whole other section on this because there's commercial interest, there's healthcare access issues. Heck, we have a lot of type 2 diabetics that can't even get insulin, and so the notion of putting these therapies out there when with the groups involved in the majority and minorities and everything, it gets real complicated. But I think Doug's primary question is a great one, but it's going to be, and Peter's an expert in this, it's going to be a lot of discussions before we see that occur. And it's outside of science.
It's great to spark the discussion and start thinking about it, though, and even put it out there for people who are thinking about hypotheses, postdocs, et cetera. where their research is going to go, because, if you think about it, 70% of the US population is overweight or obese. Their BMI is above those ranges. And so those are potential candidates to develop type 2. And that is what I'm saying. That market of individuals out there is much bigger than those who have type 1. So yeah, it's food for thought. I'm going to ask one last poll here. I'm going to launch it, and this will sort of like cap us off here, I guess. So what are the biggest challenges to cell therapy for type 1 diabetes? Scaling and manufacturing, knowing where to transplant the cells, and preventing immune rejection. So let's see what people have to say, and then let's see if you guys can weigh in on this. I guess if we're
just going to say scaling because she's in the thick of it right now, right? She's like, this is brutal. It's not sexy. Like, everyone thinks of like the big stuff, but scale up manufacturing, control, engineering controls, quality control. That's so challenging.
It's so important, and it really ties directly to the conversation we were just having about how we expand access to a therapy that works. If we can show a therapy that works, then I think all of our goal is how do we make sure that everyone who could benefit, whether they have type 1 or type 2 or another condition, has access. And I think a big part of that is manufacturing. Of course, a big part of that is the immune system. So it's a tough call on this poll question. But
yeah, and I'm going to say here, we've got 80% voted. Preventing immune rejection comes in at 86%. And so people are, I think people, that's on people's mind, is the immune rejection. And it kind of comes over here to someone's asking a question directly to Dr. Shapiro. What beta cell intrinsic mechanisms contribute the most to the death of transplanted beta cells, and do these processes converge? So, I mean, right, immune rejection is one of the biggest reasons for the transplanted beta cells not to thrive. I guess also maybe not if they don't get vascularized properly, but does anyone want to comment on that? Jump in.
It's combinatorial. You have got to, when you put your cells in, you have to have them revascularized. They've got to receive oxygen. They've got to receive nutrients, and they've got to survive immune attack. There's no easy answer to all of that. It's the whole package, but there's others more expert than I on this call that can answer better.
I sort of just was throwing this out there. I mean, a pregnancy, right, is an invasive implanted organism, I guess if you want to call it, or entity, and that's a 9-month situation. What lessons can you learn from that situation that you can use to better modify this implanting of the beta cells? Right? I mean, 9 months would be great to not have diabetes. I mean, and you've got that sort of like situation already happening normally physiologically in women for this implantation. I mean, it seems it's exactly what needs to happen with this implant.
I mean, I think that's, Doug mentioned that, the maternal fetal tolerance and what we're learning from cancer. I mean, the cancer microenvironment, these are all pathways are being identified and then being leveraged in terms of genetic engineering. So genetically engineering the cells to express markers that would mimic, how cancer cells are able to evade the immune system. A lot of the work ongoing in engineering the microenvironment is trying to basically mimic some of those features of the placenta, or the features that cancer creates, that these immune cells recognize these as being tumor, it's being abnormal, and they want to kill them, but they come in and they get re-instructed to not attack. So there's a lot of lessons that can be learned there. And I'm probably the least qualified to answer this question. I'm just very excited about it because I'm not immunologist, but we can learn a lot from that and leverage a lot of those tricks that are used.
I mean, there's a group at Stanford that's creating artificial, placentas right now. I mean, we're hoping to get that group to interface with a group from the sugar science, and hopefully, there'll be some interesting conversations to come out of that.
That's what we are trying in our consortium to understand. We are the ones that incorporate the placental derivatives into the organoids, and we are trying to reach also to genetically modify already these cells to overexpress the immunomodulatory molecules that they all already have. So if we look at the placental development and cancer development, it's more or less identical. There are a lot of similarities. So this is the things we are trying to understand and implement and apply to the bioartificial pancreas that we are trying to develop, including the vascularization, because we think that the pre-vascularizing the organoids or the bioartificial pancreas assembled already in extracellular matrix will make it easier to translate it wherever under the skin, for example, and reconnect with the blood vessels of the recipients, even to apply like a strategy of self-camouflaging. We are using the recipient-derived endothelial cells, for example.
Can I make a comment? I think I'd like to share with you my own personal experience when I was a young trainee. And Peter, you may know Rupert Billingham, who was the graduate student of Sir Peter, who really are the father of the immune privilege. And I remember vividly, we were in Finland, and Rupert said, Ali, I'm going to retire from science, but if I can give the young trainees an advice, follow the maternal-fetal immunology, which he really coined. My second thing is that we need to be aware of now across the US and Europe, there are a handful of really these unique uterus transplants are done for certain degrees of infertility. And I'm delighted to mentor one of my colleagues. These are amazing human, quote, preparation experience, because looking at the immunology of maternal-fetal in these women are just amazing source of insight into the behavior of T cells and the B cells and NKT cells in terms of the a product of the conception, which is 9 months. And of course, some of these women go on to have a second pregnancy. So this is an area. There are also probably Swedes. In Sweden, they have done more than anybody else, particularly using live donors, where you know the immune antigenic repertoire of the donor, as well as the recipient. And of course, the US has taken probably about 20 of these. I really think this is the new frontier to get insight. And I think NIAID is interested to really look at the mechanisms of these immunology during this uterus transplant with gaining insight into maternal-fetal immunology.
Yeah, there's a lot to be learned in that space. I agree. And could you mention who was the Rupert again? Could you mention the last name?
Rupert Billingham.
Billingham. Okay.
Peter, did you ever meet him in Oxford? Is Peter on?
He is, but he's muted.
I heard him speak, but in a room, but I didn't meet him one-on-one.
Amazing. He really coined the concept of immune privilege, as you know, in the field of immunology. And frankly, he also coined a field of not only immune privilege, but also maternal-fetal immunology, as well as graft versus host disease, which is, people really don't appreciate that, what he has done. The textbook of immunology in the early 70s, what he did, the immunobiology of transplantation, was only 97 pages, but it was just so packed. Up to this day, you can see the insight that he really introduced these concepts into the field.
Well, I would just say that to the young scientists that are out there listening, it's a good opportunity to dig back into the historical literature and revisit some of these concepts and papers. You never know what you can find back in the historical literature, and sometimes something pops out at you that's very useful.
Monica, the constitutional transplant is only 1 page in Journal of Nature in 1953. First author is Rupert Billingham, Brent and Sir Peter Medawar. That really created the field.
All right, I'm going to go look for this after. I love digging into that kind of thing. I would just, I'd like to say thank you so much for everyone speaking, and just in the interest of time, I know some people are super busy and they have hard stops. I think it was a really, really robust discussion, and I would look forward to the next one. I also would like to announce that together with DKNet and SPP, which is the Signaling Pathways Project Index, and the T1D Knowledge Portal based out of UCSD and the Broad, we're going to create a, or we have created, we're in the process of finessing it, the T1D based, research-based D challenge. It's really based around the use of bioinformatics tools in a consensome space, really. And registration will be open soon, and we're going to have some cash prizes for participants. So thanks for attending and driving discussion. Our next interactive town hall style State of the Science is for August 5th. And it's entitled Prevention of T1D, Remission or Cure. We're gonna have quite a few sort of biotech and industry participants. So that'll be really an interesting new style of discussion. And thank you everyone again very much for your participation. We really appreciate everything you're doing for the field.
Thank you.
Have a
you.
great
Thank
rest
you.
of
Amazing discussion.
Thank you.
Wonderful. Thank you
Wonderful.
again.
Wonderful.